This video is going to be a brief summary of permanent dipole moments. This is a topic that no one can quite agree on the name of, so you'll hear this referred to as permanent dipole moment. You'll hear it referred to as dipole moments. You'll hear it referred to as just dipoles. And they all mean the same thing. So molecules can have temporary dipoles, which we're going to deal with very shortly when we get to intermolecular forces. But usually when people say a molecule has a dipole, usually they mean a permanent dipole. Same thing as a permanent dipole moment. So what does that mean? So let's imagine you have the molecule ammonia, NH3, the active ingredient in Windex. We know from previous work that ammonia has this shape. It's the pyramidal shape, has a lone pair of electrons, which I have drawn very badly on the top. And this is a derivative of the tetrahedral shape. And if you haven't had a chance to watch the valence shell electron pair repulsion theory via CPR video, you should go back and watch that before you watch this, unless you're just feeling really confident and ready to jump in. Okay, so anyway, so this is the shape for ammonia. And it turns out that over here on the nitrogen side of the molecule, we tend to have a little more negative charge. It tends to be a little negative, a little bit negative. And on the hydrogen side of the molecule, the way I've drawn it, the bottom part, this side over here tends to be a little bit positive. Now, when we say a little negative and a little positive, we don't mean a full-blown plus one, minus one like you would have in an ionic compound like NaCl. These are molecules, so everything is kind of not nearly as, not to the extremes that you find in an ionic compound. You might be talking about a charge of negative 0.1 or 0.2 and a positive 0.1 or 0.2. But it's still enough that it's important for reasons we're going to come to in later activities. And it's always that way. So even though, as I mentioned just a second ago, dipoles can fluctuate a little bit, there's always more negative charge in ammonia on this side of the molecule. There's always a little bit more positive charge on this side of the molecule, all right? So what we do is we have a couple of symbols for that, as will not surprise you if you've been paying attention to chemistry. So over here, I'm going to switch colors. Over here on the negative side, we draw a lowercase delta with a negative sign. And over here on the positive side, we draw a lowercase delta with a positive sign. Remember that uppercase delta is a triangle that means change. And so like drawing the lowercase is delta is kind of like saying it's a little change. I don't know. At least that's how I think about it. I don't know that there's actually an official reason. But anyway, the other symbol that we draw is we draw an arrow in the direction of the negative charge because we think of it as the electrons being dragged to that side of the molecule. We put a little plus sign on the other side of the arrow to remind us that that other side is positively charged, all right? Again, this is a summary, so I'm not going deep into the how to think about the positive and negative ends, and you should refer back to your course packet, or if you're in somebody else's class, a textbook for more details on that. Okay, anyway, how do we predict the presence of a permanent dipole moment? Oh, one more thing. This stupid word moment, I really hate this. This is like a physics term. A dipole moment just means that one side is positive and one side is negative. Or sometimes we talk about a magnetic moment, meaning one side of a magnet is north and one side is south. It doesn't mean an instant in time the way it does in normal everyday language. It's just it's a physics term. And sometimes we borrow it in chemistry, but you should not think about it as like a time thing, because it isn't. It just means that there's a north-south or a plus-minus aspect to the molecule. Okay, moving on. So how do you predict this? So here's water, and when we draw the Lewis dot structure for water, it comes out like this. But we remember that when we apply the VSEPR, valence shell electron pair repulsion theory, we get this shape over here, and this is the bent or bent tetrahedral shape. And so we kind of draw it as the in this way to try to reflect the actual shape in 3 dimensions. And what happens here is, or here, let's talk about how we. So in the ammonia description, I told you what it was, but I didn't tell you how to predict it. So let's talk about how to predict it. It turns out if you look at the periodic table, if you go to the right and up on the periodic table, those atoms that are furthest right and furthest up have the strongest attraction for electrons within a molecule, all right? So it kind of makes sense because as you go to the right, you have a greater effective nuclear charge, as we've talked about before. As you go up on the periodic table, the electrons in atoms have smaller orbitals. They're closer to the nuclei. So it makes sense that these atoms that are further right and up are going to have a strong attraction for electrons, whether they are core electrons or valence electrons or shared valence electrons, as you would have in a molecule, all right? We ignore the noble gases because they don't form molecules except under duress. And so we just kind of ignore them for the most part. So we always say that the atom with the greatest electronegativity is fluorine, and then everything else falls off after that. You can look up charts of these. In my class, there's a chart in the course packet. If you're looking for this on the internet, you should Google something called Pauling electronegativity, and that'll give you I'm really not doing a great job of this. This whole concept is called electronegativity. So electronegativity, here, let's write this down here. So electronegativity is this word that we throw around a lot in chemistry, but it just means the attraction of an atom for shared electrons in a molecule, okay? So the atoms that have the strongest attraction for their own electrons, those furthest right and up, it makes sense they would also have the strongest attraction for shared electrons, and that's what we find. Again, we ignore the noble gases because they don't really generally form molecules, except under special circumstances, and even then only usually with fluorine. Anyway, that's a whole other thing. So if you look up Pauling electronegativity on the internet, it'll give you actual values for these, but in general, we're just going to think about atoms having more electronegativity as you go to the right and up on the periodic table. Hydrogen is a weirdo because hydrogen kind of belongs in group 1 and in group 7, but the way I tell people to think about it is that carbon and hydrogen have about the same electronegativity. If you look on a chart, you'll see that that's the case. So that's how I think about it. All right, so anyway, if we're comparing oxygen and hydrogen, we would say that oxygen is further to the right because, again, hydrogen and carbon are going to have about the same electronegativity as one another. And so we're going to then look on the periodic table, find that oxygen is to the right of carbon. And so oxygen is going to be the more electronegative of the two atoms you have in this molecule. Then we think about, that means that the shared electrons are going to be pulled this way towards the oxygen. Overall, what that means is that overall electrons are going to be pulled towards the bottom of the molecule. So you think of these, you think of the pull from the oxygen, the left-right side of the pulls kind of cancel each other out. So you end up with an overall downward pull on the shared electrons. And that makes this side of the molecule a little bit negative and this side of the molecule a little bit positive. Now, normally we don't draw the dipole through the molecule just because it looks weird or something. I don't know. We just don't. So we usually draw it off to the side, and that means the same thing as drawing it through the molecule. Okay, so oxygen is the more electronegative atom. It draws electrons towards it. The pull from the side-to-side pull kind of cancel each other out. So overall, you end up with a downward pull of electrons, that makes this side negative, a little negative, that makes this side a little positive, okay? All right, so now let's look at NF3, which I've drawn first as just the simple Lewis dot structure here, and then I've redrawn it in its Vesper theory predicted shape, which is pyramidal. If you look at the periodic table, and anytime you're working on these videos, I really want to encourage you just to have a periodic table open and ready to go. So if you don't have one, please pause and go grab one. But if you have one in front of you, you'll see that fluorine is to the right of nitrogen. So that means that each of the all the shared electrons are being pulled towards fluorines. Overall, that means that there's a downward pull here. And so a little positive up here, a little negative down here. By the way, and something that comes up, so the fluorine side is the negative side here. The nitrogen side is the positive side. If you were to draw this molecule sideways, there's nothing special about up and down, right? So like if you drew water like this, which we don't usually do, but let's imagine you did, the dipole now would still point towards the oxygen side. And this side would still be a little positive, and this would be a little negative. So sometimes people obsess with, oh, the dipole's got to point down. No, it doesn't. It's just whatever direction you draw it in, it has to point towards the more electronegative atom, which in this case is oxygen. In this one here, it has to point towards the more electronegative atoms, which are the fluorines. So the fluorine side ends up being negative. All right? Okay, what do we do if we have a molecule like nitrate, NO3 minus, where oxygen's the more electronegative atom, so you would have electrons being drawn outward towards the oxygens. But the problem here is the electrons end up getting treated kind of like a tug of war here. So that tug of war is between the three oxygens, and they all are going to pull equally because they're all oxygens, and they're all going to draw negatively charged electrons towards them, but they basically end up canceling each other out because their pull is equal. So that means that no side of this molecule is going to be positive or negative. So it turns out that nitrate is going to have no permanent dipole moment. Okay, no permanent dipole. And again, it's just because you've got a symmetric molecule where all the electrons are being withdrawn in such a way that that pull is being canceled out because you have it pulling in opposite directions. All right. Same thing with CO2. You have a pull towards the oxygens, but they're on opposite sides of the carbon, so that cancels each other out. It's useful to think of this like a tug of war, where CO2, you have two equally strong teams pulling on those electrons, and that means the rope's not going to move. In nitrate, you have this weird sort of three-direction tug of war, which is hard to think about, but the physics is the same, right? If you have three things spaced 120 degrees and they're all pulling equally, they're not going to move the thing in the middle. All right, same thing for tetrahedral shapes. So what I'm trying to get at is that the symmetric shapes, namely trigonal, planar, linear, and here tetrahedral, these are all going to have no permanent dipole moment, okay? So these three are the ones you have to look for and be mindful of, that they're not going to have a permanent dipole moment if all the atoms are the same on the outside. Now, what happens if you have this example that I've given here, where you have CHF3? Think about this as, okay, you've got strong electrons strongly pulled down by the fluorine. Fluorine's the most electronegative atom. Hydrogen is pretty weak in terms of electronegativity. So the fluorines, in this case, are drawing the shared electrons towards them, and there's no balancing pull up here on the hydrogen side of the molecule. So that means that overall electrons are being drawn downward here. There's a little negative here. There's a little positive here. So what I'm trying to get at here, you can't just memorize, oh, every time it's tetrahedral, it won't have a dipole moment. That's not true. You have to draw the molecule, you have to check the shape, and then ask yourself, is it symmetrical, and are the pull of the electrons to one side of the molecule all canceling out or not? Here, the hydrogen can't cancel out the pull of the fluorine, so no, it's not being canceled out. This molecule will have an observable dipole moment, all right? But if all the atoms are the same on these three shapes, trigonal, planar, linear, tetrahedral, then you won't observe a dipole. It'll be nonpolar. All right. Okay, so go ahead here and work a practice problem. Get out a piece of paper, get out your periodic table, get out your pens and your pencils, and work through this, and then we will, or I will, then work through it. So pause the video, work through these on your own. Okay, here we go. So nitrite, and I'm going to skip. I'm assuming by now that you know how to do Lewis structures, and if you don't, I'm going to suggest you go back and check that video out. Same for Vesper theory. Hopefully you've got that down. If not, go back and review on those. Anyway, this is the Vesper predicted shape. It is bent trigonal planar. Because it is asymmetric, you just have a lone pair up here on the top. You have electrons being drawn outwards towards the oxygens. So overall, you're going to end up with a dipole down, slight negative, slight positive. All right. OF2, I'm going to draw this one upward just to get at that thing I was saying earlier about it doesn't always have to be down. So this is the OF2 shape. Fluorine is the more electronegative atom, so you've got electrons being pulled up and outwards. The left to right gets canceled out, so you end up with a net being pulled up. So that side's a little negative, that side's a little positive. Okay. By the way, I know I've said this, but this shape that I'm trying to draw here is lowercase delta, and I'm not the world's greatest at drawing Greek letters, so if you need to take a look at that in a print form somewhere, you're looking for a lowercase delta. I'm just making it worse. Anyway, okay, carbonate looks like this. It is trigonal planar. And because that's a symmetric shape and all the atoms are the same on the outside, this will have no permanent dipole moment, or we could say that it is nonpolar, either one of those mean the same thing. Okay. Molecules that have a permanent dipole moment are referred to as polar molecules. I don't think I mentioned that. Those that do not have a permanent dipole are nonpolar molecules. Because we needed a few more words to make this all a little more confusing. All right. This last molecule, formaldehyde, is trigonal planar. It looks like this. And that's one of those symmetric shapes. However, the atoms are not symmetric around them. You have an oxygen, which is more electronegative than the hydrogens. So this is going to have a dipole moment pointing towards the oxygen side of the molecule. Partial negative, partial positive. All right. Okay, I hope this has been helpful. Please let me know in the comments if you have any questions or get in touch. Thanks for watching. See y'all.